So it's interesting, but you can write down what you're saying and then share.
Okay, sir.
Then it will be easy for us to go through the calculation.
So I have like a completely crazy idea regarding statistical mechanics. I will tell you someday, but because it will
yeah. Okay, this also you write down. You write down the calculation and then share it.
Yes,
then
sir.
it will be easy for us to understand.
Okay, sir. Yes, sir.
Okay, so I think it's already live. We can start.
Yeah,
Sir,
it's live. Yeah, you can start.
Sir, 1 second. Just
Yeah.
just I joined through my computer. Can you make me host again?
Yeah, sure.
Thank you, sir.
Okay, I think I have a little bit of weak internet signal today. So because of that, I will keep my video off so that at least this streaming of what I'm writing will be uninterrupted. Okay, you can see the screen, right?
Yes, sir.
Yes, sir.
Okay, so I want to start with one statement which we often see in the textbooks, that in quantum mechanics, a particle can exist at multiple locations simultaneously. So this statement you might have seen in some textbooks, or you might have been taught in quantum mechanics courses. So is this familiar to you, this statement? Yes or no?
Yes, sir.
Yeah. So I don't know, because of my internet or something, I'm getting very delayed response. Okay. Now we will spend a little bit of time to understand this statement. Okay. Or some of you can tell me, what do you understand by this statement? So first thing is, does it make sense? I mean, does it make sense to you? Not in any absolute sense, but does it make sense to you?
So it doesn't make sense to me, sir.
Doesn't make sense. Okay, then why such statements are made? Why senseless statements are made?
because quantum mechanics is very hard to comprehend for a human mind.
Okay, so it is beyond senses.
Sir, it is because of the uncertainty of the particle to stay at a particular location. So we interpret in this way. That
Okay, so this is so one answer is that is in the sense of uncertainty. Okay, any other? So what does uncertainty, in what way can we explain this statement with uncertainty? Uncertainty says that, okay, the position and momentum cannot exactly fixed for any particle, right?
yes, sir.
Okay, so does that mean that it should be there in many places?
No, sir.
Hello, sir.
Yeah.
So uncertainty, by uncertainty we mean what that is not certain, like that doesn't have probability that is equal to 1. So suppose like the particle doesn't have an well-defined position. So we cannot say that multiple locations the particle can exist, because when we say locations, then we enter into the concept of localization. And localization happens when we have a wave packet or something like that. So that has like at one position we can locate that, or around and one position. But with but the particle doesn't have a well-defined position. That's why the concept of uncertainty comes. And we cannot predict beforehand. We can a priori predict that with certainty that the particle will be localized in a position.
Okay. Okay, so let us try to take this discussion on a slightly more concrete basis. Let's say that I have a lattice. Okay. Let's consider a lattice, and this lattice has, let's say, only some 4 lattice points like this. So let me call this one as x1, this one as x2, and this one as x3, and this one as x4. Okay, so I may say that this, if the particle is in this particular position, I will call this as position states. Okay, so let me denote these position states as ket x1, ket x2, ket x3, ket x4. So these are position eigenstates. Position eigenstates of the particle. That means you have some position operator, and when you operate this on some xi, you will get the position of the particle as xi and the state xi. And this is true for I equal to 1, 2, 3, 4. So actually particle can be there only on one of these places. So now we can have a general state what a general state means is that a general state can be some state psi, which is equal to sum over I is equal to 1 to 4, some Ci into x. such that modulus Ci the square sum over I equal to 1 to 4 is equal to 1. Such states are possible, right? Ci are some complex numbers, and modulus Ci square is equal to 1 sum over I 1 to 4. So such states are legal states. Correct? So psi is an allowed state. Okay. Now, if you have psi, okay, then if you measure position, of a particle in state psi, then what will be the result? What can we say about the result?
It can be the eigenvalues, sir, with probabilities Ci.
Correct.
Ci is
So-
not Ci squared, sorry.
Correct. Then the result is 1 of xi. 1 of xi with corresponding probability mod Ci the square. Okay, for each xi, of course, you have a probability mod Ci square. So in this case, what do we say? We say that the possibility for position, okay, so position possibilities, they are x1, x2, x3, and x4. Okay, these are all possible. Does that mean that the particle will be there in all these locations?
No,
This is what quantum mechanics tells us, right? Quantum mechanics tells us that these are possible. But does that mean that the particle is there on all these locations?
No, sir.
No, right? At x1, x2, x3, x4 simultaneously. Answer seems to be no, right? Possibly this interpretation seems to be too far-fetched. Okay, there are possibilities, but how does that mean that it exists at all these locations? At best, what can we say? At best, we can say that we don't know the position. or we have no knowledge of the position. We have no idea.
So
So
we say
we,
the position is
we
not well defined.
huh?
The
Position is not well defined. Position is not known. Okay. There are multiple possibilities for position. That's what you can say, right? So it is like the outcome of a toss of a coin, we don't know, but we know that it can be head or tail. This is what is the meaning of fixing the probabilities, right?
No, sir,
This is
if the position itself by nature is not well defined, then it's not our ignorance. No, sir. It's a fact of nature.
yeah. So essentially the point is that that is only a change in the language, right? When you say it is not well defined, what do you mean by that?
No,
That means you don't know the position.
no, can we know the position like with increased experimental capabilities? Can we know in the far future? Can we know? I don't think so, because if the position is not well defined, like we cannot measure what is not well defined. If we try to measure, it will collapse. So measurement will give like xi like 1, 2, 3, 4, any one of them.
Okay. So essentially the point is that, so that means there is no superposed state is well defined in that case, correct?
Yes, sir. Like if like if one of the CI is like has some non-zero value and other CIs are like 0, then it's well defined.
Then that's not superposition. It's just one of them, right?
Yes, sir.
Okay. So essentially, what I want to say is that quantum mechanics tells you that there are different possibilities and we have corresponding respective probabilities. Okay. Okay, we can even say that, okay, position is not well defined, but that does not mean that it exists at all these locations, correct? It exists at all these locations is still far-fetched. You can say, okay, it is not defined. Okay, but it exists at all these locations is still far-fetched.
Yes, sir.
Okay, now as we are seeing this mod Ci square, that is the probability, and what is Ci?
So probability amplitude.
Ci is probability amplitude. And is a complex number. Okay. Now, if you think of the following situation. Let's say that you have some interval, let's say 0 to a or something like that, and the position can be any. So position of the particle can be anything in the interval between 0 and a. So how many positions are there? How many points are there? So there are going to be infinitely many position vectors. Like in the previous case, we have x1, x2, x3, etc. But here you can have infinitely many position vectors. Okay, so this is your position, or yeah, okay, you can call it as position eigenstates. Such that if your x operator is operating on this x, you will get that as the position x times x. Exactly like in the previous case. So now let's say that I'm interested in writing a general state. I'm interested in writing a general state. How did I write general state earlier? I wrote sum over I Ci into xi, because there are I have x1, x2, x3. But I have continuously changing position states here. That means I have to take each one of them and then multiply with that some probability amplitude. And probability amplitude is now not discrete because this x is continuously varying. And then instead of summing over, I have to do an integration. So dx, and this has to be integrated from 0 to a. And here I have to talk about a probability amplitude, right? And that probability amplitude is what I will call as psi x. That is, every x is weighted with psi of x. And this is my general state psi. My general state psi is a superposition of all the position coordinates where psi of x is your probability amplitude. And what is mod psi of x? The square. Of course, because of continuum, this is not probability. This times dx. This whole thing is the probability. Okay, so including dx is the probability. This is probability to find particle in dx around x. Okay, so this is what happens in the continuous case. So now if I say that I have psi of x, okay, if I say that I have psi of x, let's imagine that I have some psi of x. This is a complex valued function. Probability amplitude is complex valued function. So if I say that I have mod psi of x square is real and x, and let's say that it has some kind of a shape like this, what does that mean? At every value, suppose at this x, let's say this is x, and at it, this is the probability density in this case, and you multiply that with dx around this small x, that will give you the probability to find the particle in that region. Okay, so that we have psi of x, that we have a wave function for the particle, means that we don't know where the particle is in this entire region 0 to a, but we only know that any position in this 0 to a is possible, and we know the respective probabilities of this wave function. So this means that the probability, so we can only describe the particle only with respect to its probabilities in the entire region. We do not know which position the particle is. Okay, so that does not mean that particle can be there everywhere in this region. So what I want to emphasize here is that the particle exists in multiple locations simultaneously is a popular statement to represent a more technical statement that the state is in a superposition state. Okay, So if I say state is in a superposition state, that is technically a correct statement to make. And that is something that is sufficient for us to understand quantum mechanics and do quantum mechanics. Okay, so but this statement that the particle can exist simultaneously in more than one place or in multiple locations is, in some sense, it's a little bit mystical statement. Okay, so it gives you some kind of a, okay, quantum mechanics is not easy to understand, that kind of a feeling it gives. But then it essentially means that superposition is allowed in quantum mechanics. That's precisely what it is. Okay, so any questions? Okay. Okay, so now let us look at slightly simpler question, just to make sure that we understand this point clearly. So let's say that I have so let's look at some simple system like harmonic oscillator. Okay, now harmonic oscillator has got ground state. So if the Hamiltonian is operating on ground state, you will get h cross omega by 2 into ground state. And the first excited state, Hamiltonian operating on first excited state, is 3 by 2 h cross omega to 1. And you have, of course, in general, an nth excited state will have an eigenvalue n plus half h bar omega. It's n. Okay, nth eigenstate. So this is the harmonic oscillator that we. Now suppose if I say that let's say let psi be a state of harmonic oscillator such that probabilities of energies E0 and E1 are 1/3 and 2/3 respectively. Okay, so now first question I'm interested in asking is, can I write psi?
Yes, sir.
So how do I write psi?
In the energy basis, it's psi equal to square root of 1/3, 0 plus square root of 2/3, 1. Apart from that, phase vector.
Okay, so you write this as square root of 1/√3, 0 plus square root of 2/3, 1.
Yes.
Okay, but this state, okay, this state is not unique to these probabilities, because this state has, so you can write 1/√3. Remember, the coefficients have to be complex numbers. Okay, so in general, if you write, suppose in general, if I write my psi to be C1 times 0 plus C2 times 1, okay, then what is given is modulus of C1 square is equal to 1/3. Modulus of C2 square is equal to 2/3. Correct? Now C1 and C2 are complex numbers. C1, C2 are complex numbers. That means I can now take C1 to be 1/√3 into e to the power I theta 1. Correct? Then mod C1 square will be 1/3. In the same way, C2 can be √2/3 times e power I theta 2. Now theta 1 and theta 2 can be anything. So theta 1 and theta 2 are arbitrary. Theta 1, theta 2 are arbitrary. So what is the way to write this one? I would write 1/√3 times e power I theta 1, 0 plus √2/3 times e power I theta 2, 1. But I can write this as e power I theta 1 into 1/√3, 0 plus √2/3 into e power I phi 1, where this phi is equal to theta 2 minus theta 1. Now in quantum mechanics, as you know, that the state can be determined only up to a phase factor. Okay, so the state can be determined only up to a phase factor. So state in quantum mechanics is determined up to phase factor, up to an overall phase. What does that mean? That means, let's say psi is equal to, or any state phi, and e power I theta and phi are same, because they give rise to same probabilities. So I can ignore this phase factor. So what I have now is psi is equal to 1 by root 3 0 plus root 2 by 3 e to the power I phi 1. This is called, this phi is called relative phase. Phi is called relative phase. And this is something which is important. And by just giving probabilities, just like what I did now, we will not be able to determine the state correctly. But we also should give relative phases. Okay. So for example, in the above problem, I have given you that the probabilities of finding E0 and E1 are 1 by 3 and 2 by 3 respectively. Okay. That does not fix the state. Okay, that does not fix the state. Okay, so now what we should do, in addition, we must specify the relative phase or phases to fix the state, fix the quantum state. Okay, for example, if this relative phase phi is equal to pi by 2, then what is your psi? Psi can be now fixed completely, 1 by root 3 0 plus I times root 2 by 3 1. So this is fixing it completely. Okay. Now you can ask the following question. What will be the state after some time? Let's say this is so let us say that let this be the state at time t is equal to 0. So what is the state after state at time t. So how will you find that out? You know that how each one of this will vary with time, right? So your psi of t is going to be equal to 1 by root 3 e to the minus I by h cross into energy is h cross omega by 2 into t into 0 plus I root 2 by 3 e to the minus I by h cross 3 h cross omega by 2 into t into 1. Because each one of this is an energy eigenstate, and they, so you have h cross cancelling here, h cross cancelling here. So that's equal to 1 by root 3 e power minus I omega t by 2 0 plus I root 2 by 3 e to the power minus I 3 omega t by 2 times 1. Okay. Now, so you can pull out, you can write this as e to the minus I omega t by 2 into 1 by root 3 0 plus I times root 2 by 3 into e to the minus I omega t. This is an overall phase, so can be ignored. And we have psi of t is equal to 1 by root 3 0 plus I times root 2 by 3 e to the minus I omega t 1. Suppose you want to find out what is the expectation value of the position. Okay, so let's say you want to find out x position as a function of time. So that is given by your psi of t, x, and psi of t. Okay. Now, how do you do this expectation value of position? So this is an operator, and if you remember your harmonic oscillator, you can define an operator A as okay, so I can say that this x can be written as h bar by 2m omega into a plus a dash. Okay, so that is, I can write this as h bar by 2m omega into, we have 1 by root 3 0 plus I times root 2 by 3, 1 into a plus a dagger into 1 by root 3, 0 plus I times root 2 by 3, 1. Okay, so now what happens when a operates on 0, you will get 0. A operates on 1, you will get 1. Okay, so first thing is 0. Second thing is I root 3, I2 by 3, 0. Root 1 into 1, that's what we get. Now a dagger on 0 is 1 by root 3, 1. And a dagger on 1 is plus I root 2 into root 2 by 3, 2. But anyway, on the left hand side, we have 0 and 1 only. So 2 will not contribute. So you can see that 1 by root 3 into I into 2 by root 3. So that is equal to h bar by 2m omega into 1 by root 3 I into root 2 by 3. So 0, 0 is 1. Then you have 1, 1. That is plus I 2 by 3 and 1 by root 3 and 1 and 1. And all other terms will become 0. Sorry, there is this term. In this case, it will be e power I omega t. Here it is e power minus I omega t. So we should not remove that. So you can see that a operating on this one is 0, a operating on this one is 0. That means here I have e power minus I omega t. And this is 1. And this also has e power minus I omega t. So now what happens? 0, 0. This has e power minus I omega t. And this has e to the power I omega
Hello, sir.
Yes.
So will there be root over, sir? Like x cap is equals to root over h cross by 2m omega? I think you are missing the root over, sir.
Yeah,
Square
yeah,
root.
yeah, correct. Okay. So now we can write this as root over h bar by 2m omega into okay, I can pull this factor out. That is I root 2 by 3 into e to the plus I omega t and e to the minus I omega t is 2 cos omega. Okay, so this root 2 will cancel with this root 2. So we have square root of some I 2 by 3 into h bar by m omega into cos omega. Okay, so what is that we are getting? We are getting the expectation value of t. Okay, so this expectation value of this one
Hello, sir.
is
So expectation value is something we can like measure like deduce from the experiments. So how can it be I can stay there, sir? Iota. We have an observable like,
Yeah.
position.
That's right. So I think we have to be careful. So here I have to put a minus I because I'm taking adjoint of that. Okay. So if I take a minus I there, then what happens is this becomes minus, correct? This becomes minus. Okay, so that means this is not cos omega t. This is minus 2i sine omega t. Okay, so this is minus 2i sine omega t. Okay, so
Yes,
this
sir.
minus I and I is, that is 1. So I have 2 by 3. So this I will not be there. 2 by 3 h bar omega. Okay, so let me write it here. So x of t is equal to 2 by 3 square root of h bar by m omega into sine omega. Okay, so 2 by 3 square root of h bar by m omega is like an amplitude, and this is a sinusoidal event. This is somewhat, I mean, this is exactly like what you find in classical harmonic oscillator solution, right? The expectation value of this one is exactly like classical harmonic oscillator solution. Okay, so so is it surprising that this so what happens, suppose if you are in any one of the for example, if your state is if the state is, let's say, 0, then what is your expectation value of position? That is 0, correct? And this is true for every energy state. Okay, and every energy eigenstate is also true for n. Whereas when you take a superposition state, that is 0 and 1 superposition state, of course, I have chosen probabilities with 1 by 3 and 2 by 3. Okay, then you have classical harmonic oscillator like solution for the expectation value. Correct? So what does that mean? What will happen if you have I have chosen only 2 energy eigenstates in the superposition. If we choose, let's say, 3 superposition states, let's say 0, 1, 2, then of course I have to specify probabilities for each one of the states, and also I have to specify 2 relative phases. Only then I can fix the state completely. Correct? So will the result be different? Or is there something special to this 0 and 1?
So 0 and 1 are stationary states. So stationary states when linear combinations are not stationary states.
Correct. They are not stationary states. But I'm
Stationary
asking
states.
0 and 1, linear superposition of 0 and 1, is it in some sense special? Or if I take 0, 1, 2, 0, 1, 2, 3, for everything I will get this kind of oscillatory behavior.
Yes, sir. Time dependence cancels out for a stationary state, sir.
Correct.
Because expectation value of a stationary state is constant in time. That's one of the features of a stationary state.
Yeah. My question is, even if it is a non-stationary state,
Yes, sir.
superposition of 0 and 1, is it special, or any superposition would have given this classical like behavior?
Any superposition will give, sir. Sir,
Yes.
I think any superposition will give.
Okay, so if I take 0, 1, 2, then also I will get the same thing.
Yes, sir. Because that unfaced theorem, I guess, expectation values will follow classical rule. I think from that I am thinking, sir.
Yeah, but what about stationary states in that case? Stationary states, see, expectation value depends on the state, right?
Yes, sir.
But if you take stationary states,
Yes,
the
sir.
expectation value is 0 for that.
Yes, sir.
So it's not following the classical behavior.
Yes, sir. Sir. That also true.
So
Let me think that. So you are asking whether 0 and 1 any specialty is there or not? Okay, 0.
you can see that suppose instead of 0 and 1, you take a superposition of 1 and 2, for example. You
They
will
are
get the
also
same.
oscillatory, sir. It's like two level.
Yeah. So it is this oscillatory solution you will get if you take superposition of any two consecutive levels. Because the energy level difference is only h cross omega, right? So your relative phase will always be to the power minus I omega.
Yes, sir.
So you take any consecutive levels, okay, you will get the same result.
Yes, sir.
You take either 0, 1 or 1, 2 or 2, 3, whatever you take, you will get the same result. Okay. That is one thing. Second thing is, if you take, suppose if you are, let's say that you have some state which is some superposition of this these energy eigenstates, then if you write down expectation value of x as a function of t, then you will always have only either sine omega t or sine 2 omega t or sine 3 omega t. So there will be only harmonics of that omega. Correct? In general, it will be like that. Because imagine if you have 0 and 2, for example, then there will be sine 2 omega t term. Okay. So it will be periodic, and it is like you are doing some Fourier series. Okay, so in general, you will have a fundamental frequency omega, and then its harmonics will be there. Okay, so that is fine, because that is like you have a periodic function of some fundamental period omega. It need not be sine or cos, but it can be expanded in sine or cos. Okay. Now, We can ask yeah. Okay. Now I think in some problem solving sessions, I think some of you have shown this. Now suppose if you ask a question that okay, you have now found out x of t. Now if you want to find out delta x of t. Delta x of t, how do you find out? You find out x square at time t minus x square or x at t the square. Okay. So this may be a little bit involved, so I will not do it here because you have to do some calculation. You have to take x square and then do the same thing. Okay, so I will leave this exercise as an exercise for you to do. But then I want to ask the following question. That is, if you take delta x, this is uncertainty in x. Okay. So let us take the same state. That is, for the state 0. Okay, so I think I chose this state to be psi is equal to 1 by root 3, 0 plus I times root 2 by 3, 1. Okay. Now for this, what will be your x square average at time t? So that is equal to 1 by root 3, 0 minus I root 2 by 3 into e power I omega t 1. So this is bra vector of psi of t into a plus a dagger the whole square. So there is a coefficient h bar by 2m omega, and you have a square plus a dagger the square plus a dagger plus a dagger a. So this is a plus a dagger the square, and then I have 1 by root 3, 0 plus I times root 2 by 3 e to the minus I omega 1. Okay. I'm just doing this calculation only to show some h bar by 2m omega into 1 by root 3, 0 plus I root 2 by 3.
Sir,
Yeah.
Sir, can we do this like we can find the average energy in the state, and we know half will go to kinetic energy and half will go to potential energy. So from that, if we take to that kinetic energy term to left hand side, from that x square expression we can find. Or I'm saying Like in any state, the total energy, half will be from kinetic energy, half will be from potential energy. Correct, no, sir?
Yes.
So this case, total energy will be 1/3 of h cross omega by 2 plus 2/3 of 3 by 2 h cross omega.
Yes.
So its half will be kinetic energy. So like half
But-
of total energy equal to half m omega square expectation value of x square.
Yeah. So, but so that actually what you get is a time averaged quantity, right?
Oh, evolution I will not get. Yes.
You will not get time dependent factor.
Okay. Okay.
And sir, I didn't get like why half the energy will go to kinetic energy and half will go to potential energy, sir.
See, in a time averaged thing, there is something called virial theorem.
Yes, sir. Yes, sir.
Okay, which in time averaged sense it will become half of that will be kinetic and half of this. That is also valid for time average.
Yes, sir. But that depends on the like potential form, like how for a central potential, how it's depending on the power of R. If R to the power n. So
Correct.
depend on n. So like here it's squared. That's for this specific case we are getting like half to will go to potential, half will go to kinetic, but not all of the problems.
No,
we
not
can do that.
always. Not always. No. A dagger, this becomes plus 1 by root 3 0, and that is 0. So a square, that is 0. So a dagger square, root 2 and root 3. Six times 2 plus a dagger.
Sir, can I suggest a method, sir?
Hmm.
Sir, can I use the commutator of A and A dagger? Like it is identity, no, sir.
Correct.
So A dagger we can write as 1 plus A dagger
Yeah.
Hello?
So you will.
A, and A dagger A is number operator, no, sir.
Correct. A dagger A is number operator. So
A dagger we can replace it with identity plus number operator. So identity and number operators are easy to work with, no, sir. So like we don't have to do this calculation always like first multiply the operator with A dagger then A or
So a dagger minus a dagger A is 1. So
A dagger we can write 1 plus
a
A
dagger
dagger. A dagger is n, so number of
1 plus a dagger A. It is 1 plus 2 times a dagger.
yes. So I think the identity will leave it unchanged, and the number operator will spit out the n and like that kit. Okay.
Okay, so a square on 1 is this, and a dagger square on 0 is a dagger square on 0 is this one, and a square on 0 is also 1, and a square on 1 is also okay. So let us try to write it like this. A square plus a dagger square is 1 plus a dagger A by 3 0
So twice A dagger is, sir.
twice a dagger. 2 by 3 e to the minus I omega t 1. One has to, of course, do the calculation to get the final result. Root 2 by 3 for I omega t 1. Now a square and 0 and a square and 1, both of them will vanish.
Zero.
A dagger square and 0. A dagger square and 0 is 1 root 2 by 3 2 plus. Okay, so you have 1 plus a dagger a and 0 is 0, right?
Sir, like a dagger square will also act on like K to 1 also. So
Yeah, a dagger square and set 1 will become I root 2 by 3 root 6
yes,
times
2, 3, 3, yes.
3. Okay. Then you have, so a dagger a on 0. 1 plus 2 a dagger a is simply 1.
Plus 2n plus 1, sir.
Yeah, 1 by root 3. One, 0 plus I times root 2 by 3 e power minus I omega t into 3 times 1, correct?
Yes, sir.
Okay, so that is much. So there is here also I have e to the minus I omega t that I don't require anyway. Okay, now you see this is 0 here and I have 0 here. So that is h bar by 2m omega into 1 by 3. And then I have 1 here and 1 here. That means plus I root 2 by 3 e to the power I omega t into I root 2 by 3 into 3 e to the minus I omega t. So that is equal to square by 2m omega into 1 by 3 minus 2. Oh, this is minus. So there is minus I, so that is plus square by 2. So there is no time dependence.
No, sorry. Sir,
Ah.
e power I minus I omega t, sir. Okay.
Yeah, here plus I omega t, right?
Yes, sir. Okay, sir. But why there is no time difference?
So now we'll write delta x of t to be equal to h bar by 2m omega minus what was our x of t? X of t was 2 by 3 omega sin omega. So that is 4 by 3, 4 by 9, h bar by m omega sin square omega. We can pull out h bar by 2 m omega. This of course under square root. 1 minus 8 by 9 sin square. Okay. Anyway, so I want you to verify this calculation once. But even if this calculation is there, one important point I wanted to make here is that suppose you try to find out, let's say that you have, so this x of t, okay, delta x at different times, right? So you suppose you ask the question, what is delta x at time t into delta x at time t prime? Okay. So if you use this expression, then you will see that this is also not equal to 0. Okay. Even with this calculation, we can show that this is not equal to 0. What does that mean?
So there is a correlation in time in the the standard deviation of the x coordinate position. There's a time correlation, sir.
No. What does that mean in terms of your uncertainty relation? If this is not equal to 0, that means there seems to be some uncertainty in position at t and at t prime, right?
So by uncertainty, what do you mean by uncertainty, sir? Here,
it can never be 0, 1 uncertain.
See, I have calculated this delta x exactly like what we calculated delta x delta p, right?
Yes, sir. Yes.
So I have calculated this delta x of t also like that. This means if you are talking about an x of t, an operator at x of t, and another operator x of t prime, okay, they should not commute with each other. Okay, because we can go from here to there and from here to here.
So isn't the uncertainty principle valid for two different observables? Here we are using the same observable.
Yeah, I am getting this result, you know. That is why I am asking what does that mean. There is nothing saying that it should be two different. See, x at t and x at t prime are like two different operators.
Okay, sir.
And they are not commuting, and hence there is an uncertainty for them.
So how can there be two different operators in Schrodinger picture? We're using the Schrodinger picture. The operator doesn't evolve in time, but the state does.
Yeah. So that means if when there is an uncertainty like this, and I want to understand this, I have to go to Heisenberg picture, where I have to make operators time dependent and see if the operators at two different times commute or not. Correct? This uncertainty in any picture, of course, uncertainty is defined with expectation values, and expectation values, time dependence of expectation values can be obtained either from the time dependence of the state or time dependence of the operator. So far I have used Schrodinger picture, and then I have seen the state vector changing with time. I found out expectation value. I found out uncertainty. Okay, then that shows that delta x at t and delta x at t prime are, when you multiply them, it's not equal to 0. Right? So if you want to understand that in terms of commutation, then you have to go to Heisenberg picture.
Okay.
Sir,
Yes.
is this because, sir, the position operator does not commute with Hamiltonian? So when we go to Heisenberg picture, sir, that's why these
Correct.
operators, they don't commute to different time.
Correct. So it evolves. It evolves in time. If a position commutes with the Hamiltonian, then in Heisenberg picture, it's constant of motion, right?
Yes, sir. Yes, sir.
Yeah. So I'm trying to just show you a case where this uncertainty, in fact, whatever I have done, you can do with the momentum also. So momentum at time t and momentum at time t prime is the same momentum operator. But whatever we have discussed now with position, you can do the same discussion with the momentum also. And you will see that momentum at two different times, they don't commute. And hence there is, see, this is precisely the reason why when you say that you have, let's say your Hamiltonian is time dependent. Okay, if your Hamiltonian is time dependent, then your time evolution has to be carefully done, because Hamiltonians at two different times may not commute with each other. Okay, so because of that, time evolution has to be carefully done. That is where you have this time ordered product and all that will come into picture. In general, operators at two different times need not commute. Okay, that is the message that we have to understand from this calculation. Any operator, you cannot take it as granted that they commute at two different times. In general, they don't commute.
Sir, like, do we need to really go to the Heisenberg picture? Because in Schrodinger picture, we can have the total time derivative of the expectation value of an observable. And if the observable doesn't explicitly depend on time, then and the observables is commuting with Hamiltonian, commutator is 0, then we can say that it's like conserved in time. No, so time evolution is conserved in time evolution. So do we really need to go to the Heisenberg picture?
See, the conservation you can say even without going to Heisenberg picture. But then if you want to show that what is the commutator of these two things, because you know there is a relation between commutator of x at t and x at t prime and the uncertainty delta xt delta xt prime, right? That general, you see, you have a general commutation. Suppose let's say A and B are two operators and A, B don't commute and they have a commutator value. Then that value of the commutator of A and B and the uncertainty delta A, delta B are related, right? So if you want to understand whether this uncertainty what we are deriving here through this picture is same as that relation is general. So then you have to find out what is the commutator of x at t and x at t prime. You have to go to Heisenberg picture.
Okay, sir. But sir, like, isn't it like a correlation function? Like, I'm not sure. Like, I need to study the subject more, but isn't it like correlation function, like time correlation? Like, if we know some still like observables value, like outcome at t, value at t, then at t prime there will be a correlation between the observables values.
Yeah, but correlation is different. See what the correlation means. Suppose let's say that you have some x of t, okay, and you are going to take x of t and then take x of t plus some tau and then take an average of this. Okay, so then you get some correlation which is a function of tau. For different taus, this correlation is different. This is what correlation is, right? So here there is no such averaging that is done. So if
yes,
you are trying to imagine this delta x of t is like x of t here, okay, even it is just a multiplication of these two, that's all. There is no averaging or anything done here.
Okay, so but in delta xt there are expression values, means x squared expression value and x expression value
Yeah,
squared.
so how you are getting delta xt is different, but after getting delta xt, this is just a product of delta xt and delta xt prime. Now we are not looking at how delta xt is correlated.
Okay, sir. Okay, sir.
Yeah.
And sir, I think for like a single system correlation, we cannot like define correlation because like for a bipartite system, we can use correlation. So, but for a single system, we cannot like define correlation.
Yeah, I mean time correlation you can talk about for anything that is varying in time. Okay, so that is fine, but that is not related to this uncertainty. What we talk.
Okay, sir. But sir, time correlation is used in like non-equilibrium phenomenon. No, sir.
Correct, correct. Yeah. Okay, so I think we can stop.
sir.
Yeah.
Sir, in the beginning, sir, that problem, we found that expectation value of x, no, sir, and we found it is oscillatory, sir. Is
Yeah.
it special? You said no, either 0, 1 are the special state.
Yeah,
What is
actually
that?
there is nothing special about 0, 1. Only thing is that x operator will only connect adjacent states.
Oh, okay, sir.
That is so if you look at the x matrix representation of x operator in the energy basis,
Yes, sir.
you will have non-zero elements only in the first diagonal, not the diagonal, but just first upper diagonal and first below the diagonal.
Yes, sir. Means I plus 1 element. I plus 1 element.
I plus 1 and I minus 1.
Minus
that
1.
element will be there. So
Yes.
they will only connect adjacent states. Because of that, you take any two consecutive states, you will get the same behavior.
Yes, sir. And this it is not diagonal also in the energy basis. The operator cannot be diagonalized, right?
Yeah, it's not diagonal. That is another reason why you can say that X and Hamiltonian don't commute.
But A dagger A is diagonalized, right?
A dagger A is diagonal.
Sir, I didn't understand this, sir. Like, why can't be diagonalized? X can diagonalized?
No, in the energy basis, X is not diagonal.
Yes, sir. But in X basis?
In X basis, it is diagonal. In that, Hamiltonian is not diagonal.
Yes, sir. Yes. Actually, sir, at that time, the power went off and I got disconnected. So I could follow. Hello?
At which time?
During like in the middle, like you were discussing the Hamilton, like the harmonic oscillator problem.
Uh-huh.
And before that, like you started with the like with continuous like X will continuously continuous basis concept. I don't know.
I
like
was
at the
I was only trying to
Hello, sir?
connect. I was only trying to connect what I discussed with the lattice in a continuum case and show that what wave function is only the the probability amplitude for each of the x.
Okay, sir. But sir, when you drawn the lattice, that reminded me of tight binding model, sir. Like the
Yeah.
hopping. So how hopping is like the like the particle is not simultaneous in all the locations, but I said that it's not well defined. The position of the particle is not well defined, but in tight binding model there is a concept of hopping. Like suppose it's in x1 now, and after like after t time it will go to x2. Nearby it will go to nearby sites. Hop to
Yeah.
nearby. So how that is understood from there, sir?
No, there is interaction there, right? So
Yes,
there
sir.
is
Like
some
electron wave
interaction.
function overlap.
So interaction is there, and hence the probabilities will evolve in time.
Yes, sir. Yes, sir. Like sir, by interaction we are using non-interacting systems. No, sir. Means which is interacting with whom? Like we have one particle. No, sir.
No, it's interacting with the lattice, underlying lattice. On the lattice, you have ions, and
Okay, sir.
ions are interacting with this electron.
Like crystal field theory, like sir.
Yeah.
Okay. But so like in the beginning,
Crystal
I was
field theory is different, but this is just a periodic potential
yes.
on the lattice.
Okay, sir. Okay, sir. The crystal field theory, we have a three-dimensional crystal, no, sir? Like
Correct.
Like sir, block wave, no, block wave.
Yeah, block wave is there, but so basically in all these crystalline systems, you have an underlying lattice which presents a periodic potential to the electron, and electron in the periodic potential will have energy levels which form in terms of those bands, and these bands will I mean, even you can talk about these bands which form either by like whatever that chronic penny model we have, no, like that you can have bands, or you can think of atomic levels and they coalescing to become bands,
yes,
and
sir.
then
But
talk about each of the electron in different energy levels within the band.
yes, sir. Sir, like the Pauli's exclusion principle is like having some effect here, no, sir. But
Correct.
we also have photonic crystals where like photons, like although they are bosons, they can have like a periodic potential. So
That is basically periodic refractive index change.
yes, sir. But bosons are like different, no, sir. Like
Yeah, but that is in terms of the periodic potential, you can say that any particle, whether it is a fermion or a boson, quantum mechanically it is same. Only when it comes to populating the energy levels, you will have to use a Pauli principle or not.
yes, sir. Sir, just one last question, sir. Like in the beginning, I was mentioning about the interferometer and spin analogy. So, sir, how can we use the concept of interference in case of spin, sir?
See, interference is what in this particular case for you, interference in Mach-Zehnder interferometer is uh, all the particles going to one detector, right?
Yes, sir.
Okay,
Like
so
we do it like with one particle, sir, like one spin or one photon. Then
correct. I mean, you will, I mean, in order to demonstrate the interference is there with one photon, you will not be able to demonstrate, right? If it is going to D1 or D2, it may be, if one photon means whether all of them are coming to D1 or D2, you will not know, right? You have to use anyway many photons.
so like with like time being encoding, like suppose I transmit one photon now and after 2 seconds I will transmit another photon. Like I will use like
okay,
a
one
photon
photon
source
at a time.
at a
That's what
time.
you're
Yes.
saying.
Yes.
Yeah. So so equivalent of thing how you should do in spin, we have to see.
Yes. How like and in the Maxwell interferometer we can vary the path length by like using mirrors or like using a phase shifter or using like a longer optical fiber. But how can I do with spins? That is the question I have.
See, the only thing that you have to do is you have to use magnetic fields only, spin.
Yes, sir.
So you have to
Magnetic
use,
fields are like the beam splitters, like standard non-uniform magnetic fields.
correct, correct.
Okay, sir. Okay, sir.
Okay, so we can close.
Shall I stop the recording?
Yeah, yeah.
Okay.
And